Today, we're going to continue solving oblique triangles. This means a triangle that does not have a right angle in it. We're going to use our standard deployment of the names of things. Side A will be opposite angle alpha, side B will be opposite angle beta, and side C will be opposite angle gamma. Sometimes we'll refer to alpha, beta, and gamma as capital A, capital B, and capital C. So sometimes we'll use capital letters for the names of the angle and lowercase letters for the names of the sides. But in any case, A is opposite A, B is opposite B, and C is opposite C. A is opposite alpha, B is opposite beta, C is opposite gamma. That's going to be our standard use of lettering. In the solving oblique triangles game, we had to come up with a new set of tools to solve the triangle. The one carryover we have from solving right triangles is that the sum of the angles in a triangle is 180 degrees. We no longer are going to be given a right angle, but we still have the good rule: if we know two angles, we should subtract to find the third angle. Always go after the easiest piece of information first. And if you have two angles, you have three angles, because you're just subtraction away from having three angles. Last week, we talked about the generalized form of the Pythagorean theorem. And that was the law of cosines. That's shown down here on the left. C squared is A squared plus B squared minus 2AB cosine C. If C is a 90-degree angle, then cosine of 90 degrees is equal to 0. And so it takes out this term, and C squared is equal to A squared plus B squared. So the law of cosines is like the Pythagorean theorem, but for oblique triangles. This means we have multiple versions of the law of cosines for C squared, B squared, and A squared. We also have law of cosines for angles. So we could just take each of our three law of cosines and solve them for angle C, angle B, or angle A. The new piece of information that we want to get today is the law of sines. The law of sines says that the ratio of the sine of an angle to the side opposite that angle is constant in any triangle. Or, with an algebraic abbreviation, sine alpha over A is sine beta over B equals sine gamma over C. But if we want to say it in words, and we have an unnamed triangle, the ratio of the sine of an angle to the side opposite that angle is constant in any triangle. The ratio of the sine of an angle to the side opposite that angle is constant in any triangle. If one of our angles is a right angle, let's say angle C is a right angle, then we'll have the sine of 90 over C is equal to sine A over A. Since sine of 90 is equal to 1, we'll have 1 over C is sine A over A. We can solve this for sine A, and we'll get sine A is opposite over hypotenuse. So this works out. So if I have sine A, if C is a 90-degree angle, this still fits our right triangle trigonometry definitions. If C is 90 degrees, I could write sine A over opposite is sine of 90 degrees over hypotenuse. And if I solve, since sine of 90 is equal to 1, I can solve for sine A as opposite over hypotenuse. So just like our law of cosines is just a generalized law or a generalized Pythagorean theorem, the law of sines is kind of a generalized sine equals opposite over hypotenuse. Once we have the law of sines is easier to use. So what we want to practice is, as soon as we can use the law of sines, we should use the law of sines because it's much simpler. So the law of most of the rules that we have are going to be set up to get that fourth piece of information, and then we can use the law of sines. So once we have 4 pieces of information about the triangle, we're off to the races. We could use the law of sines and our life becomes simpler. The 2 cases that we covered last week, where we have 3 sides or the 2 sides and the included angle, in both of those cases, we can't use the law of sines because I don't have a set of opposite information. If I have side A, side B, and the included angle C, then I can't use the law of sines. I don't have an angle opposite one of those sides. Or if I have all 3 sides, I don't have any angles, and I can't use the law of sines. So once we have a set of opposite information, a side and the angle opposite that side, then it's time to use the law of sines. Partially because we can't really use the law of cosines if we have that scenario. We kind of can, but it gets really messy. So for example, if I have side C and angle C, I can plug it in. I'm looking for A. I can solve using the law of cosines, but it's going to be quadratic. In A squared, B squared, presumably we have. A is we don't have, B we do have. Cosine of C we can find, and C squared we can find. But it ends up being quadratic, and that's just way too much effort. So our thinking is going to be, use the law of sines as soon as we have a set of opposite information. A and angle alpha, side B and angle beta, side C and angle gamma. All right. So here are the 4 cases that we could come across. The two we looked at last time, where you're given 3 sides. You're going to have to use the law of cosines for any of the angles. I recommend that you start with the largest for no other reason that we got to start somewhere. And if you just say, I was going to start with the largest, that takes a decision away. You don't have to worry about it. For side angle side, that's 2 sides in the included angle. You use the law of cosines to find the side opposite the given angle. That's your only choice. You really can't do much else with that set of information. So for that first piece of information, you use whatever you can. The third case is actually 2. If you have angle side angle or angle angle side, this is 1 side and 2 angles, either 2 angles in the included side or 2 angles in the side opposite one of those sides. If you have 2 angles, you have 3 angles. You're just subtraction away from 3 angles. So subtract to find the third angle. Then you have an abundance of information. Use the law of sines. And then the fourth case, side-side angle, is when you have 2 sides and an angle opposite one of those sides. This is called the ambiguous case of the law of sines, because it could result in 0 triangles, 1 triangle, 2 triangles, or 1 triangle. I know I said 1 triangle twice, but there's 2 ways we could end up with 1 triangle. So the reason that this is the ambiguous case is that it could be 0, 1, 2 or 1 triangles. We can use this set of information, 2 sides and a non-included angle, to possibly build 2 triangles, or possibly build no triangles at all. So that's when we're going to have to be careful. We're going to have to recognize that we're in the ambiguous case of the law of signs. It'll be pretty clear from context. Once we understand why this case is ambiguous, it's pretty. It'll be pretty clear when we have to know which of the 4 cases we'll be in. Any questions before we get started with an example? So last week we did side, 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 and side angle side for the law of cosines. Let's take a look at the example, our first example here. Let's suppose that angle A is 105 degrees, angle B is 43 degrees, and side B is 30 feet, and we want to solve the triangle. So the first thing we want to notice is that I've got 2 angles. As soon as we have 2 angles, let's subtract to find the third angle. So the first reaction, if we have no other instruction as to what to do first, we have 2 angles. So subtract to find the third. So the first thing that we're going to do is say angle C is 180 minus 180 minus 105 minus 43. I have not been able to do arithmetic all day, so we'll just do 180 minus 105 minus 43, 32. That's our third angle. Make sure I'm in degree mode, because if I was in radian mode, it would come out to 32 degrees. It's not, it doesn't care what these numbers are. I wasn't using trig functions. All right. So first thing we notice, if we have 2 angles, we should just subtract to find the third angle. That should be like automatic. I'm just trying to program you with that response. Now at this point, I have a set of opposed information. I have side B and angle B. So now we can use the law of sines. Since we have opposite information, with side B and angle capital B. So now it's time to use the law of sines. So now it's time to use the law of sines to either find side A or side C. Doesn't matter which one. We're going to do the same thing for both anyway. But I'm going to start with A because A is going to be the biggest side, for no other reason that it's the biggest side. So I'm going to set up my ratio of sine of B over B. So sine of 43 degrees over 30 feet is equal to the sine of 105 degrees over the side we're looking for, A. Now I just need to solve for A. So I'll multiply by the 30, or I'll flip things over, divide by the 30, and multiply by sine of 43. A is going to be 30 times the sine of 105 divided by the sine of 43. And we'll just drop this into our calculating machine and do 30 degrees. Okay, I did put it back in degrees after my shenanigans. 30 times the sine of 105, close parentheses, divide by the sine of 43, close those parentheses too, because we're building good habits. And then we'll get 42.5 feet. I can use the same technique for side C. So I'll say the sine of 43 over 30 feet, sine B over B is equal to the sine of 32 degrees divided by C. And so we'll solve for C similarly to what we did for A. C is going to be 30 times the sine of 32 divided by the sine of 43. So I'm just going to press second enter and trade my 105 for a 32. Let me get 23.3 feet. In this problem, I chose to use 43 degrees and 30 feet because none of that information has been rounded off. Once I use 42, once I have come up with 42.5, that's been rounded off. I could use it to solve for side C, but I'd rather use the information that was given. Use as much given information in any calculation as possible. So we could, at this point, once we have A, we could use 105 degrees and 42.5 feet to solve for C. So once we have A is equal to 42.5 feet, we could do sine of 105 over 42.5 is equal to sine of 32 divided by C. So I could say C is equal to 42.5 times the sine of 32 divided by the sine of 105. So 42.5, let's just clear it. 42.5 times the sine of 32 divided by the sine of 105. And we don't get any difference until the tens, hundredths, thousandth place. So we're pretty safe. So in this case, we were safe in rounding. I should rephrase this. We could have done. And we have safe rounding in this case. Any questions? The other reason I chose to use 43 and 30 is that that stuff was already in the calculator. I just had to change my 105 to a 32. So no problem. Any questions? if you recall, last time we started off with a law of cosines. So if you would recall, one of the examples from last time I had an 894 for A, B is equal to 850, and C is equal to 810. In this case, law of sines is off the table. I don't have any angles, so I don't have that opposite pair. I don't have that opposite info. So we had to use the law of cosines to find our first angle. We chose to find angle gamma first for reasons. So we used the law of cosines to find angle gamma is equal to 55.3 degrees. At this point, we have a set of opposite information, the 810 and the 55.3. So at this point, we can use the law of sines. Now that we know the law of sines, and now in this problem that we have a set of opposite information, we can use the law of sines. So we could set up sine of 55.3 over the side opposite, that 810, that's the opposing information or the opposite information. And I could say this is equal to sine of alpha over side A, 894. We'd have to solve for alpha is going to be the sine inverse of 894 times the sine of 55.3 over the 810. Last week, we didn't have this law of sines technology. We had to use the law of cosines again. But then we subtracted. Because once we have two angles, we subtract to find the third one. So I'll do a sine inverse of the numerator, which is actually, I don't need that because it's all multiplication. 894 times the sine of 55.3. I do need to close these parentheses, and then I'll divide by 810. Close the sine inverse, and I'll get 65.1, just like we had before. Then once we have two angles, we could subtract to find the third. Since we're armed with calculators, there's not much difference between using the law of cosines and the law of sines. Once we know what to type, there's not that much to be gained by using the law of sines versus the law of cosines. So once you have an abundance of information, the best law to use is the one that you can and the one that you think of. So if it occurs to you, if in a side case, if it occurs to just use the law of cosines twice and then subtract for your third angle, then that is what you should do. You should never finish solving a triangle, say, oh, I should have done this. Delete that save and then go back to a previous save and then continue that way. Just keep going. Any questions? Let's talk about why the side-side angle case is ambiguous. So what we have here in the SSA case are two sides and the angle opposite one of those sides. So this is two sides, that's the SS, and the A is the angle opposite one of those sides. Two sides and the angle opposite one of the sides. So for example, let's suppose that we have given an angle alpha, side C, and side A. So I have two sides and the angle opposite one of the given sides. So the parts that we have are the angle opposite one of the given sides, the side opposite the given angle. So here's how I want to refer to things. In this case, since we're given angle alpha, side A, I'm going to call this the side opposite the given angle. Clever name for the thing that is the side opposite the given angle. So this is the side opposite the given angle. The soga. Side C, I'm going to refer to as the other given side. So we'll have the given angle. Let's refer to this as the given angle. So we have the given angle, the side opposite the given angle, and the other given side. That's how I'm going to name the parts in the side-side angle case. It's like a little orc family. Soga, Ga, and Ogs. Soga. Ga. Ogs. So this is what we call them in Orcish. We, like I speak Orcish. So let's draw what we have. So put a horizontal line. This is going to be where side B will go. I'm going to draw angle alpha. So if this is the side where, this is the line where side B will go, and I draw alpha in this corner here, alpha, the given angle, then that means since the side opposite the given angle is A, that means the other given side is here, C. So here's the other given side. And alpha is the given angle. And the side opposite the given angle has to connect from the end of C and reach the line where side B will go. The side opposite the given angle goes here, opposite the given angle. Here are the things that can happen. I had a note card right here, just for this purpose. And it's gone. Nope, we'll have to talk about it. So here are the things that could happen. I said earlier that we could have 0, 1, or 2, or 1 triangle. One thing that could happen is that the side opposite the given angle is too short to reach the line where side B will go. So it could be that I try to draw A and it's just too short to reach the side where B will go. So we'll get 0 triangles. If the side opposite the given angle is too short if the side opposite the given angle is exactly long enough to go from the end of C down to the line for B, then we'll have 1 right triangle. So 1 right triangle, if the soga is just the perfect length. We'll end up with 2 triangles if the side opposite the given angle is long enough to make 2 triangles. So if the side opposite the given angle is a little bit longer than is necessary, then we can end up with 2 triangles. So if this is where we start and the side opposite the given angle is greater than the height, so it's a little bit longer, then I can make 2 triangles, one going this direction, where I have this obtuse triangle, and one going the other direction, where I have this other possibly obtuse triangle. Oops, I shouldn't cover up the triangle that I'm trying to make. So we end up with 2 triangles if the side opposite the given angle is a little bit longer than the perfect length, but not too long. Two triangles. So if the SOGA is longer than the perfect length, but not so long that we get one more triangle, if it's longer than that perfect length, but not too long, then we'll end up with two triangles. As we can see, we could swing this, if it goes a little bit past the line where B is going to be, we can get one triangle if we swing it one way towards alpha, and another triangle if we swing it away from alpha. But it could be that the side opposite the given angle is too long to make two triangles. Judging by how I just decided where I'm going to put the side opposite the given angle, or how long I'm going to make the side opposite the given angle and how I measured it compared to C, you can tell what this one case is going to be. If I attach this side, I can make one triangle by swinging this way out here, but if I try to swing it towards alpha, if I try to swing the side opposite the given angle towards alpha, I won't be able to make another triangle. It'll go right past the alpha, and I won't have alpha in my triangle anymore. It'll have gone too far. I did it again. I covered up the thing that I'm trying to draw. So this triangle does not have alpha in it. So if we have just the right length, I can make one triangle out here with the side opposite the given angle away from alpha. Then I can swing the side opposite the given angle towards alpha and make a second triangle. But if that length is too much, then I get one triangle. And when I swing the side opposite the given angle towards alpha, it just goes all the way around. I lose the angle alpha. So we get one triangle if the side opposite the given angle is too long. So the bottom end of where the side opposite the given angle can be is just the height of the triangle, the shortest distance from the end of C down to the line where B will go. The shortest distance is perpendicular, and that will be the height. Now, the shortest distance from the end of C to the line where B is creates a right triangle. So we can set up a relationship using right triangle trigonometry. We can say that the sine of alpha is the height over the other given side. So we can solve for the height and say that the height is the other given side times the sine of alpha. Oh, the given angle. I switched from A alpha C to the generic names. So when we say that the sine opposite the given angle is too short, that means it's less than the height. We get one right triangle if the side opposite the given angle is equal to the height. We'll get two triangles if the side opposite the given angle is greater than the height, but less than the other given side. And we get one triangle if the side opposite the given angle is too long or greater than the other given side. So there's 0, 1, 2, or 1 triangles with this given set of information. If you imagine, if we line all these things up, if we put a number line, we're going to have down here a 0. We're going to have up here the height of the triangle. Then we'll have the heights, and then up here we'll have the length of the other given side. This divides the number line up into these three regions. If the side opposite the given angle is between 0 and the height, we get 0 triangles. If we're exactly equal to the height, we get 1 triangle. If the side opposite the given angle is between the height and less than the other given side, that's when we'll have 2 triangles. And if the side opposite the given angle is greater than the other given side, we're back down to 1 triangle. We can always calculate the height by taking the other given side and multiply the sine of the given angle. Here's why we don't need to bother calculating the height of the triangle by taking the other given side and multiplying by the sine of the given angle. And also why we don't even need to bother figuring out how many triangles there are going to be. If we just assume that there might be 2 triangles, we can just proceed and the numbers will tell us what case we're in. So we don't need to figure out what case we're in. We just proceed as if there are going to be 2 triangles. And the numbers will let us know what case we're in. So it's not that we need to figure out what case we're in, how many triangles there are going to be. We just have to know that there's a possibility of 0 triangles, 1 triangle, 2 triangles, or 1 triangle. We don't have to figure that out to move forward. We can figure out the number of triangles, but we don't need to. We don't need to figure out how many triangles. We just need to know that it could be up to 2. All right. Let's take a look at an example. I had an example written down and now it's gone. All right. Let's suppose that angle alpha is 72 degrees. Side B is 83 somethings. Let's use meters. Let's have big, nice, big, giant triangle. The QR code at the bottom of my notebook is so when I scan the notes, the calculator knows where, or my phone knows where to scan. That's all. So suppose that alpha is 72. That's the given angle. Let's suppose that B is 83 meters. That'll be the other given side. And let's suppose that the side opposite the given angle, A, is equal to 67 meters. So here's our given angle. A is the side opposite the given angle. And the 83 is the other given side. How's everybody okay? I haven't stopped and checked in for a while. All right. So remember, whatever angle we're given, if we have the side opposite the given angle, then the other side is going to be the other given side. Notice that we are not going to be able to use the law of cosines to get started. Law of cosines is right off the table because I have alpha and A. If I wanted to use law of cosines, it would end up, I guess it's not off the table. I misspoke. We just don't want to. It would end up being quadratic in C, and we don't want that. Quadratic. It would be quadratic, and we don't want that. So we're going to use the law of sines. We're going to recognize that this is two sides and the angle opposite one of those sides. So we're going to recognize that this is the ambiguous case. We could try and figure out how we could calculate the height and compare the side opposite the given angle to the height to figure out the number of triangles. Let's do that, and then let's see why we didn't have to do that in the first place. So the height is the other given side multiplied by the sine of the given angle. So we'll take the other given side, 83, and multiply by the sine of 72. And you can see that I calculated this so I could write the problem. And so the other given side multiplied by the sine of the given angle is going to be 78.9. At this point, we'll notice that the side opposite the given angle is less than the height, so there is no triangle. I invent these abbreviations and I just don't bother using them. The SOGA. So the ruling on the field, no triangle. There's a hand signal from the refs for no triangle. It looks like this. So if you're a ref and you come up with no triangle, you'd be like, you make a triangle with your hands and you go, and you just shake your head back and forth. I mean, you're mic'd up and you have like a little transmitter. So you could just be like, all no triangle. But you have to make the hand signs too. So you're like, all no triangle. So in case you're watching competitive trigonometry, that's what you should look for. No triangle. Now I said we didn't have to calculate the height. Let's suppose that we forgot to calculate the height. We do know that there could be 0, 1, or 2, 0, 1, 2, or 1 triangles. But I told you that the numbers that got your back. Let's start using the law of sines and see what happens. So I'm going to set up my opposite information. I'm going to say the sine of 72 divided by the 67 is equal to the sine of B divided by side B, 83. So once again, we already know that there's no triangle. We're pretending that we didn't calculate the height. We just forgot to calculate the height. And we just proceeded to try to find angle B. Oh, I should use angle beta. Fixed. So beta will be the sine inverse of 83 sine 72 divided by 67. No problem. So we grab our calculating machine. We didn't notice that there's no triangle. Forget how to turn our calculator on. And we do the sine inverse of 83 times the sine of 72, close parentheses, divided by 67. Close parentheses, hit enter, and we get an error. A domain error. What we're trying to do is find the sine inverse of a number bigger than 1. So more than just an error. If it was a syntax error, we don't get to conclude anything. That's the calculator not understanding what we're asking it. But this is a domain error. So this is an error domain. And the calculator always shouts its errors because it's all caps. It can do lowercase letters, you can see down here, but if there's an error, it just shouts at you. What we're trying to do is if we look at the parts that we're trying to take the sine inverse of, if we just look at the sine, if we just look at the 83 sine 72 divided by 67, that's more than 1. So notice what we're trying to do is find the sine inverse of 1.17. But no angle has a sine of 1.18. The opposite side can't be greater than the hypotenuse. The range of sine is from -1 to 1. So the domain of inverse sine is from -1 to 1. The range of sine is from -1 to 1. So the domain of sine inverse is from -1 to 1. Another way to think about it, the side opposite cannot be greater than the hypotenuse. The hypotenuse is always the biggest side. Opposite can't be greater than hypotenuse. So opposite divided by hypotenuse is always less than or equal to 1. The hypotenuse has to be the biggest angle. The other way that this fits is that notice the 83 sine 72 is the height of the triangle, and the 67 is the side opposite the given angle. If that ratio is greater than 1, if the height divided by the side opposite the given angle is greater than 1, that means the height is greater than the side opposite the given angle. Or equivalently, the side opposite the given angle is less than the height. However you say it, the alligator wants to eat the height. So good news. If we forget to calculate the height and we just proceed to try to find that first angle, we'll get a domain error. And then we'll say, hang on a second, something fishy is going on here. And then we'll notice that we'll check that we typed everything in incorrectly. Typed everything in correctly. That's terrible. Typed everything correctly, drop the in part. English is a terrible language. We should just use -1. Anyway, the 83 sine 72, that's the height, and the 67 is less than that. So that ratio is greater than 1. We try to find the sine inverse. We can't find the sine inverse of a number greater than 1. So there is no angle. Side A, the side opposite the given angle is too short because it's less than the height. It's just dangling there at the end of the side B, and there's no way to reach the side C. Any questions? So if you forget to calculate the height business, don't worry. The numbers have got you. As soon as you started writing this down, your colleague's like, oh man, I see where this is going. You didn't check the height. You didn't check the error domain. And your calculator's like, I told you. I'm just kidding. Your calculator doesn't know what you're doing until you actually hit enter. So let's change things up a little bit. Let's suppose that alpha is 72 degrees. Side B is, I'm going to use the same setup, 83 meters. And side A, so here's our given angle. Here's our other given side, OGS. And so A is going to be our side opposite the given angle. Soga. Minus D&D character. Soga Oggs, the triangular orc. So I know what I want to happen. I want this to be a two triangles case. And so I want the side opposite the given angle to be greater than the height. So more than 78.9, but less than the other given side. So I'm going to make A equal to, let's go with 79, that's too close. Let's go with 81 meters. I didn't make a good enough angle that it's going to give me a lot of room. What did I say? 81. So the first thing that we have to notice is that we have a set of opposite information, and we have another side. So we have a side opposite the given, a given angle, a side opposite the given angle, and another side. Ambiguous case could be 0, 1, 2, or 1 triangles. Now we can figure out which case we're in by calculating the height. So the height is always going to be the other given side multiplied by the sine of the angle. So the other given side is 83. And the sine of the given angle is, the given angle is 72. And we know that 83 sine 72 is 78.9. So we notice that the side opposite the given angle is greater than the height. So we get at least one triangle, but less than the other given side. So we get two triangles. So the side opposite the given angle, 81, is greater than the height of 78.9, but less than the other given side at 83. So we got two triangles. That's helpful to know going in, but we don't need to know that going in. Helpful to know, but we don't need to know. It's helpful to know, but we don't need to know. We could just jump in and use our opposite information, say the sine of 72 over the 81 is the sine of B over 83, and solve for B. And that's going to be the sine inverse of 83 sine 72 divided by 81. 83 sine 72 divided by 81. So let's calculate. We'll do this, sine inverse of 83 sine 72, close the parentheses, divide by 81, close parentheses, and we get 77.0. That's only one angle, and we should have two values of beta. Notice that what we calculated here, if I take out the sine inverse parts, we're doing sine inverse of 0.975. We use the sine inverse, which means we found a reference angle. So we're going to treat this as a reference angle. So we're going to have a 77.0 degree reference angle in quadrant 1 and quadrant 2. The reason that we have to do this is that angles from quadrant 2 still fit in triangles. In quadrant 2, we have angles between 90 degrees and 180 degrees, and we can still have a triangle with an angle from quadrant 2. So we have two values of B. I've got B is 77. Oh, I suppose I should be, beta. There we go, beta, because I used alpha. 77.0 degrees, this is going to be in quadrant 1. Now that I've got two angles, I got 77, the 72, I can subtract to find the third. So my gamma is going to be 180 minus 72 minus the 77. My first gamma is going to be 31. Now that I have gamma, I can go and find C. I want to use as much given information as possible. So I'll say sine of 72 divided by 81 is sine of gamma divided by C. So C is equal to 81 sine of 31 divided by sine of 72. So glad we have calculators and we don't have to look this stuff up in like reference books that we carry around. Or use like a slide rule. 43.9, we'll call it. And this is a length or side, so 43.9 meters. That's one of our triangles. Has a beta of 77 degrees and a gamma of 31 degrees and a side C of 43.9. But just like skywalkers, there is another. Unlike skywalkers, there's only two. Just like skywalkers, if you're cynical about the most recent trilogy, there's only two. We have to have the beta for a 77 degree reference angle in quadrant 2. So our other beta is going to be 180 minus 77. Or 103. Now that we have two angles, our other gamma is going to be 180 minus 77 minus the 103. Oops. 72. Yikes. 180 minus the 72 minus the 103. Five. Very flat triangle. But that's okay. We have the sine of 72, still a triangle, over 81 is equal to the sine of 5 over C. So C is 81 sine of 5 divided by the sine of 72. So if you're in the two triangles case, you solve for that first angle, treat it like a reference angle in quadrant 1 and quadrant 2. On Thursday, we'll talk about this last case where we have one triangle because the side opposite the given angle is greater than the other given side. So we'll look at the case where the side opposite the given angle is greater than the other given side. That's going to be a one triangle case. Here's what I recommend you do in the meantime. Earlier I said you don't have to calculate the number of triangles before you begin. You just begin. If we're going to have 0 triangles, the numbers tell you that. They say, hey, there's a domain error with your sine inverse. What are you doing? If you get an angle for your first angle, treat it like a reference angle and put it in quadrant 1 and quadrant 2. If you don't know that there's going to be 2 or 1 triangle because you didn't compare the side opposite the given angle to the other given side, just do that anyway and see what happens. So do this problem where the given angle is 72 degrees, the other given side is 83 meters, and the side opposite the given angle is 90 meters. Don't use 90 because then it looks like a right angle. You'll get confused. 100 meters. Make it something bigger than the other given side and see what the numbers do. All right, that's going to do it for today. I will see y'all on Thursday. Everybody have a good couple of days, and thanks for playing.